Right, we are coming to the next presentation, and while there's just a little change, I'm happy to introduce the Stochastic Mechanical Systems and Automation Laboratory from the University in Patras. I guess many of us know Professor Spilios Fassois. At least I know him very well because we're running a lecture series for more than 10 years. And yeah, it's fascinating with statistics. It's usually numbers and whatever, not things which fascinate too many people. But now suddenly they appear here on stage and are going to show us what you're going with all that data being processed. It's going to be on the basis of a video because I guess you could not bring all the equipment here, but I read a little. Patras is next to the sea, and next to the sea there's ships and ship structures. There was also many years back a plenary here telling us how they deal with the ship structures. They have a lot of similarities to aeronautical structures somehow, but they have chosen a ship structure. And on this one, I guess it's a model structure, and on this one they are, I guess, harvesting a lot of data and processing those ones from a statistical point of view. And that is hopefully just what comes to my mind before we're heading over here to hear what is happening all in the details. Aha, something is happening here. Good.
Hello, my name is John Sakelariou, and I will not say much as the video is almost 5 minutes. You will see a real-time problem that includes damage detection, classification, and restoration. We decided this presentation to be given by our PhD student, Ilias Iliopoulos. You will see his name once we are ready with the presentation. So, we have to wait for some second too. It's a very simple, as we wait, it's a very simple statistical time series methods that actually is based on the power spectral density of the measured signals, which is estimated online. And and then based on a classification procedure, it says if there is a damage or not. Technical demon. Forget the presentation. Forget the presentation. Oh, forget it. Okay, we'll see only the video as the presentation is not possible to be shown on the monitor. Okay, let's start with this.
My name is Ilias Iliopoulos, and I'm a PhD candidate in the Stochastic Mechanical Systems and Automation Laboratory of the University of Patras. I'm going to present a demonstration of a structural health monitoring application using vibration-based statistical time series methods. First of all, let's take a look at the structure. It is an in-scale, free suspended hull of a ship that consists of vertical and horizontal beams which are joined by numerous bolts and rivets. The input signal is a stochastic force signal generated by an electromechanical shaker, and the response signal is measured by this single accelerometer in this specific position. The response signal is presented in this graph. From this measurement we can extract the power spectral density graph, which indicates a lot of resonances in the testing bandwidth, which is between 0 and 820 Hz. The aim of the demonstration is to detect and classify damages A and B, which are caused by loosening these specific bolts, through the power spectral density based method. This method is associated with the changes in the response spectrum and operates in two phases. The baseline phase, where the reference signals are obtained under healthy and damaged states of the structure, and the inspection phase, in which the method should determine the unknown current state of the structure. Currently, the structure is under healthy normal state, and this is indicated from the green line, which is between the red lines. The green line represents a sensitive to damage characteristic quantity, and the red lines are the critical limits corresponding to the healthy state of the structure obtained in the baseline phase. I will loosen bolt A and cause damage A. I'm operating the damage detection method, and after the acquisition of a 10 seconds signal, we expect to see the green line out of the limits. The method operates successfully, indicating the damaged state. The next step is to classify the current damage, and in this case I'm using as a reference the spectrum corresponding to damage A. Also, the red lines here, the critical limits, correspond to the class of damage A. So, the green line is expected to be between the limits. Correctly, the method classifies the current damage as damage A. Let's check the method's results. If I choose as a reference the spectrum corresponding to damage B. We see that the method correctly does not classifies the current damage as damage B, and the green line is out of the limits. Now I'm going to bring the structure back to the healthy state. After tightening the bolt A, I'm operating the damage detection method, and as you noticed before, we expect to see the green line between the limits. The method operates successfully, and now I will move forward to the loosening of bolt B and try to classify the current damage. Now I will use as a reference the spectrum corresponding to damage B. So after the 10 seconds acquisition, we see that the method successfully classifies the current damage as damage B. Thank you very much for your attention.